All right, well, let's go ahead and get started with this. So Thursday, a week from now, we will have our real exam. The exam will also have 20 questions, just like the sample did. And it will have, I think, gee, I forgot, either 1 or 2 extra credit questions. So, but it'll have the basic 20, and it'll follow the same essential format that this one did. Because we did our quiz that had the integrated spectroscopy, we will not have integrated spectroscopy on this exam, although as you saw from the sample, there are a number of spectroscopy questions. Any questions before we get started? All right, we started off here with some very simple nomenclature. Here we have 3 compounds, and we simply want to write the IUPAC name. Our first one is a disubstituted benzene. When you have a disubstituted benzene, the first thing you have to do is figure out where carbon number 1 is going to be. Now, we're going to name this as a derivative of benzene. So we have an ethyl group and we have a methyl. Alphabetically, the ethyl group is going to win. So this is going to be our carbon number 1. Now, if we proceeded numbering around the ring counterclockwise, the methyl group would be in carbon 2, 3, 4, 5. If we go clockwise, it would be in carbon 3. 3 is better than 5. So we have an ethyl group in position 1 and a methyl in position 3. We're going to assemble our name alphabetically. So it's going to be a 1-ethyl, 3-methyl benzene. We can also name this as a derivative of toluene. Remember, if you name it as a toluene, by definition, the methyl group is going to be carbon 1, so that would make it 3-ethyl toluene. Do you have your sample for me?
Yeah, I'm just writing it
Okay. Any questions? Simple, happy little nomenclature. Our next one is a tri-substituted benzene. Once again, we want to try to come up with carbon number 1. Because it's tri-substituted, we're going to look for our lowest number sequence at the first point of difference. Now, our alphabetical winner here is going to be bromine, but if we let that be carbon 1, and we went clockwise, nitro would be 2, 3, 4, and methyl would be 5. So that would be 1, 2, 5. If we let nitro be 1, bromine would be 2, and methyl would be 4. 4 is less than 5, therefore we're going to let the carbon bearing the nitro group be number 1. Once you've done that, you just need to figure out what you've got and then assemble your name. We're going to have a bromine here in carbon 2, a methyl group in carbon 4, and a nitro in carbon 1. We will assemble the name alphabetically. So the first is going to be our bromine, then our methyl, and then our nitro. So we're going to have a 1-bromo, 4-methyl, 1-nitro benzene. 2-bromo, 4-methyl, 1-nitro benzene. Any questions? All right, our last one here isn't a benzene, it is a cyclohexadiene. Now, this really goes way back to last semester, where you named dienes in 6-membered rings. Remember when you're numbering an alkene, the rule is that the first two numbers, 1 and 2, must proceed through the double bond. It starts at one end of the double bond and proceeds to it, through it. And you want to do that so you get your lowest number sequence. If we started here and went around this way, this would be carbon 1, 2, 3, 4, 5, 6, so we'd have a methyl group in carbon 6. If we started up here, so that would be carbon 1, 2, 3, 4, 5. 5 is better than 6, so we want to start our numbering over here. Once again, this is a 1,3 cyclohexadiene. And all we have to do is say that here at carbon 5, we have a methyl group. So, putting our name together, we're going to have a 5-methyl 1,3 cyclohexadiene. Straight from 234. Any questions? Now your exam will also have 3 simple nomenclatures just like this, about the same degree of difficulty. Any questions? All right, our first multiple choice question here. Which of the following is true regarding the infrared spectra of carbonyl compounds? Okay, carbonyl compounds, carbon-oxygen double bond. Selection A, aldehydes and ketones typically show a strong CO stretch at about 1710. That's about. Aldehydes might be a little bit higher than that. Some ketones are a little less than that. But around 1710, 1720 is a pretty good shot. So yeah, that sounds good to me. Any questions? Next option here, aldehydes will typically show 2 sharp absorbances at about 3,400 reciprocal centimeters. Well, yes, aldehydes do have unique sharp absorbances. That's how you can tell it's an aldehyde. But what's around 3,400? That's the OH stretch, isn't it? That's not an aldehyde. Aldehyde CH stretch will typically be in the region about 2750. Our next one. Carbonyl absorbance from a ketone is often not seen because of symmetry issues. Well, we know that symmetry issues are important in the infrared. If you have a stretch that is perfectly symmetrical, it is not infrared active. You can see it in what's called Raman spectroscopy, but in the infrared, it does not absorb at all, if it is perfectly symmetrical. However, a carbonyl with a carbon and an oxygen, you can't get much more unsymmetrical, can you? It's a carbon, it's an oxygen. That's why it's such a big absorbance in the IR. So symmetry issues are important, but certainly not for the carbonyl. And that means D and E are obviously not correct. And A is our best answer. Any questions? If you have your sample. Thank you. Any questions? All right, mass spec. Chlorine and bromine are interesting in the mass spec. Bromine consists of two isotopes, one at 79 and one at 81, an average around 80, and about equal distribution. Chlorine has two isotopes, 35 chlorine at about 75, 37 at 25. So this means if you have a compound containing a chlorine, it's going to have two molecular ions in the mass spec, because 75% of it will have chlorine 35 and 25% will have chlorine 37. So our ratio here is going to be 3 35s for every 1 37. So if you think about it then, if you're going to look at the actual molecular weight of the ion, it must have this same ratio, simply 3 to 1. For every 3 35s, you will have 1 37. Yeah?
Is that the case for bromine too, then?
For bromine, because it's 50-50, you will have a 1 to 1. Fluorine is going to be 100%. Iodine, I don't remember. But chlorine and bromine are the classic ones. All right, on your sample exam, I forgot to include, parenthetically, M over Z of 91 for the base peak. So you might write that in there, but it's here now. Remember, M over Z, that's mass to charge. Everything that we deal with in the mass spec will have a +1 charge, even though you can have +2s, but we're just dealing with +1s. So really, this is just a mass of 91. We're looking at toluene, and we're looking for the base peak. Our first option here, this is the toluene radical cation. This is what you get if you take toluene and you simply rip an electron off. It has the full mass of toluene itself, minus a tiny bit for the electron. Toluene itself has a mass to charge of 92, not 91. So right away, toluene cation is not going to be what we're looking at. In fact, with the mass spec of toluene, you do see a peak at 92 due to this guy, but it's minor relative to the base peak. Our second one here, this is our friend, the tropylium ion, C7H7 plus. Tropylium ion, we remember from way back in 234, was one of the classic examples of a stable carbocation. You can take tropylium fluoroborate, and it's soluble in water. I mean, it is such a stable carbocation. It also has a mass to charge ratio of 91, so this is a really good possibility. Our next one here, this is the benzyl carbocation. Now the benzyl carbocation also has a mass to charge ratio of 91, and it is also a definite possibility here. If we knock the methyl group off of toluene, we would get phenylcation. Phenylcation is C6H5 with a mass to charge of 77. So that's not 91. We can rule it out. Plus, the phenylcation is a miserable cation, very unstable. You can see it in lots of, you'll see it in the mass spectrotoluene, but it's a minor peak relative to the others, very unstable. Likewise, this is the phenyl radical cation. Again, it's still at 77, but it's still very unstable. So we have two possibilities here. We're looking at tropylium or benzyl. Benzyl is a nice stable carbocation, but tropylium is 1,000 times more stable. The base peak is typically going to be the most stable carbocation that you can form. Any questions? All right, we're looking at the infrared of benzyl alcohol. We want to look through this list and come up with the major bands. The way I would do it is to simply look at the molecule and predict what we should see. Let's start up at the high end and work our way down. At the high end, the first band we would expect to see is going to be our OH stretch. We know that that's a very intense broad stretch, usually centered around 3,500 reciprocal centimeters. So we're looking for that. The next thing, as we work our way down, we would expect to see sp squared CH stretching. Remember that sp squared CH stretching occurs on the high side of 3,000, typically around 3,100. So we would expect one of those. On the low side of 3,000, we would get our sp cubed CH. Typically, we get a band or two right around 2,900. Again, that's a simple sp cubed CH stretch. And the last thing that we would look for here would be our carbon-carbon stretch. And those typically occur around 1,600. So we expect 3,400, 3,100, 2,900, and about 1,600. The one that seems to work here is going to be this guy. Any questions? All right. Which is not true regarding the spectra of 4-methylbenzonitrile? Benzonitrile is basically a benzene ring with the nitrile group attached. It's a legal name. And here we have a methyl attached in the para or number 4 position. All right, so which is not true? So, in the proton NMR, the phenyl group will appear as 2 doublets. Now this is 1,4 disubstitution or para-substitution. Remember, in para-substitution, a real signature for it in the infrared, in the proton NMR, is that we get 2 doublets, one for each of the hydrogens. If you think about it, this hydrogen, no hydrogen here, but it's adjacent to one over here. So this guy splits this one into a doublet. Likewise, this guy is split by this one into a second doublet. With 1,4 substitution, you typically see very nice clear array of 2 doublets. This is in the benzene region, so between 7 and 8 parts per million. So this one looks good. C13 NMR. In the C13 NMR, we'll have 2 singlets and 2 doublets in the aromatic region. Now, aromatic region, remember in C13, is down further, 120 up to 160, something like that. We will have 2 singlets and 2 doublets. Now remember, when we see splitting in C13 NMR, it's due to the hydrogens that are attached to that carbon. So one hydrogen will split the signal into a doublet. If we have no hydrogens, we will get a singlet. If we had 2 hydrogens, we will get a triplet, etc. So here we have carbons bearing hydrogens, and each of those will appear as doublets. So this is one doublet, has 1 hydrogen attached. This is the other doublet. It also has 1 hydrogen attached. These and these are the same. Here we have carbons that bear no hydrogens. So they will show up as singlets. So our prediction for the C13, 2 singlets and 2 doublets. And that sounds right. Any questions on that one? Remember, the splitting comes from the hydrogens attached to the carbon. Iris spectrum will display a significant absorbance at about 2200. Well, what in the world's at 2200? Well, that's our carbon-nitrogen triple bond stretch. Quite often, alkyne stretches don't show up very well because of symmetry, but carbon-nitrogen, well, that's pretty asymmetric, and that shows up very nicely. We get a beautiful carbon-nitrogen triple bond stretch, yep, about 2200. Our next one, in the proton NMR, the methyl group, so that's this guy, will absorb at approximately 2.2 parts per million. Now remember, a simple group like a methyl, just sitting there by itself, would be 1-ish, 1.5-ish. If you put electron withdrawing groups on it, it moves it downfield to a larger value of delta, larger part per million. Here we have a benzene ring. Benzene ring is mildly electronegative, and it shifts it down very nicely, again, to about 2.2. This looks correct to me. Therefore, our last one here must be wrong. In the mass spec, the base peak will most likely be m over z equals 91. Well, that's our tropylium. Clearly, this is the wrong one. The reason is that there's virtually no way we can take this molecule, rip off the nitrile, and make a tropylium ion out of it. We would have to somehow transfer a hydrogen from one end of the molecule to the other. It's just not going to happen. The whole process for doing that is not good. we will not see that. What you'll probably see is this guy losing hydrogen to make the molar equivalent of a benzyl carbocation. But it will not be a 91. Any questions? All right, this next question, in fact, the next group of questions, deals with carbon 13, and it really just kind of tests your notion of symmetry. Being able to appreciate symmetry is very important in organic. Which of the compounds shown below would show 5 peaks in the decoupled C13 NMR? Now remember, decoupled means we don't have to worry about splitting. So the real question is, how many different types of carbons are there in each of these compounds as far as the C13 NMR goes? So let's just look at them. Our first one here, we are dealing with a 5-membered ring, so that's 5. We have 2 methoxy groups that are going to be identical. So we're going to have 5 for the ring, 1 for a methyl group, a total of 6 unique carbons in the C13 NMR. The most highly shifted, of course, is going to be the carbonyl here. It's a ketone, so you probably look for it at about 207. Remember, ketones and aldehydes shifted way up there. But 6 carbons, and we're looking for 5. Our next guy here, this is an aldehyde. So let's do a simple carbon count. We have the methyl group, we have this guy, so that's 3. And the methyl for the methoxy group gives us 4. 4 carbons, that's not 5, so forget it. It's an aldehyde again, this carbon in the C13 is going to be highly shifted, somewhat over 200. Any questions? This is methyl pyruvate. We have 2 carbonyls in here. One is an acyl carbonyl and the other is a ketone. We have a total of 1, 2, 3, 4 carbons as far as the C13 goes. This ketone carbonyl will be above 200. This is an acyl carbonyl. Remember, that's less. That's about 175. Nonetheless, we only have 4, and that's not 5. Any questions? All right, this next one, before I say it, think about it. How many unique carbons do we have for the C13? Well, clearly, we have an acyl carbonyl and a methyl group, right? So that's 2. We have 6 carbons in the ring, but the ring has symmetry, doesn't it? So these carbons and these are going to be the same. So we're going to have 1, 2, 3, 4 carbons from our ring, 5, 6 from our side chain. Total of 6 carbons, not 7. And finally, that leaves our last one here. This is methyl acetoacetate. We'll talk a lot about this in chapter 19 and 20. We have a methyl group that's 1, 2, 3, 4, 5 carbons. Sounds good. This is our correct answer. We have a ketone carbonyl, 207, an acyl carbonyl, 172, and then we have our methylene here in the middle. That's our triplet at about 46, and here's our quartet at about 50. Any questions? All right, let's do another symmetry problem. Here we have just a generic di-substituted aromatic, and we're substituting in our 1, 2 position, and they're the same. What would we see in our C13 NMR? The thing to do here is to appreciate the symmetry. Because it's 1, 2, and they're the same, we have a plane of symmetry right across the ring. If we have a plane of symmetry, that means that everything on the top is the same as the bottom, so we only have to really deal with one side or the other. Now remember, we're looking at the hydrogens that are attached to the carbons. Where the side chain is, where X is here, there are no hydrogens, so that's going to be a singlet. This is ortho to the attachment. It has one hydrogen, so that's a doublet. This guy, again, meta to this now, one hydrogen, it's a doublet. There's our singlet. This has one hydrogen, so it's a doublet. This has one hydrogen, so it's also a doublet. So what we're looking for is a singlet and 2 doublets in our array of answers. And I think B works. Any questions? All right, let's do another one. This is 1,3-dichloropropane. The question simply is, how many unique carbons do we have for the proton-decoupled C13 NMR? So we're just talking about peaks, single peaks. Well, let's start off somewhere. This carbon here, this is bonded to a chlorine and to a CH2. So that's a carbon. Next to it, here in the middle, we have a carbon that's bonded to a carbon on both sides, and this guy has 2 hydrogens. And over here we have a carbon bonded to a chlorine and a CH2. But because we have symmetry right down the middle here, this one is the same as that one, and it doesn't count. So quite simply, how many carbons do we have? We have 2. Now let me change the question here just a little bit. If I gave you the proton NMR of this, the proton NMR, what would we see? Well, we just made the argument that this CH2 and this CH2 are the same, right? Both of them are next to what? This guy in the middle is also a CH2. So these hydrogens are going to be split into a triplet because they're adjacent to these two CHs. We have two CHs, splits this signal and this one into triplets. Okay? Look at the hydrogens next to it. How about the carbon in the middle? Well, this is a CH2. How many hydrogens is it adjacent to? Well, it's got two here, and it's got two here. They're the same, they're identical, but they can have different spins, can't they? Therefore, this guy sits here and says, I'm next to 4 hydrogens. And so this signal is split into 5 peaks. 4 hydrogens, 5 peaks. So we'd expect a triplet for these two, area 4, and a pentet for these two, area 2. Any questions? Think about that one. It's kind of a cute problem. All right, a couple more. Here we have a cyclic ether. Every carbon is adjacent to 2 oxygens. We're back to C13. But let's just start with 1. This carbon is adjacent to 2 oxygens. This guy would also be adjacent to 2 oxygens, and so would this one and this one. All of these are the same. Therefore, as far as the C13 NMR goes, we have 1 type of hydrogen. Carbon. If we looked at the proton NMR, this would show up as a singlet because it's not adjacent to any carbons bearing hydrogens. Everyone got that? 1 peak. And we'd also have 1 peak in the proton NMR. Finally, here we have a fused, a 6-member ring fused to a second 6-member ring. Again, we're looking for the number of unique carbons. For this, I think it's easiest to take my beautiful little drawing and let's just turn it flat. Sit on it for a little bit so it flattens out. This makes it easier. Makes it easier to appreciate the symmetry. Once you get it flattened out, you can easily see that we have a plane of symmetry across this way, and we have a plane of symmetry across here. So we have 4 sections in our molecule, and they're all going to be the same. So if we just deal here with 1 group, 1 of the 4, they're all going to be the same. We're going to have our bridgehead carbon here, this guy, and this guy. 3 unique carbons in the C13 NMR. Any questions? All right, this is our last spectroscopy question, I think. And it has to do with the infrared. What I've done is I've given you the infrared, and I'm simply asking which of these is consistent with this infrared spectrum. All right, let's start off with benzaldehyde. Benzaldehyde, we have a benzene ring. We would expect to see sp squared CH stretch at about 3100. We would expect to see carbon-carbon stretching at about 1600. We would expect to see a nice carbonyl, 1700 or so. And we would expect to see aldehyde CH at about 2750. We look at our spectrum. We do have a carbonyl. We don't have anything on the high side of 3000. Don't really have anything here at 1600. And we don't have the aldehyde doublet. Therefore, this is not consistent. This next compound, this is what's called an acetal. We'll learn about this when we do the chapters on aldehydes and ketones. This actually hydrolyzes very easily in aqueous acid to give a carbonyl compound. This would give an aldehyde. But the way it is now is the acetal. We would expect to see saturated CH from all these, and we do have that. We might see an OCH somewhere, but the one thing that this has that this one doesn't, this has the carbonyl, and it's missing here. So this guy we can rule out easily. Here we have a methyl ester, a derivative of acetic acid, and here in carbon 2 we have a nitron. Now the carbonyl and the CH2 would be consistent with our peak here at 2900, our carbonyl here at about 17 or so. But the one thing it's missing here is our carbon-nitrogen triple bond. Remember, this should show up here about 2200, and it should be a nice, strong peak. This one doesn't work either. Let's skip D, and let's go to E. E, well, we have a ketone carbonyl. That's good. We have nice saturated CH here at 2900, but this should give us both a double bond stretch and sp squared CH. We don't see either. Well, this one is wrong. Obviously, D is our correct answer. We have only saturated sp cubed CH and a really nice ketone carbonyl. Any questions? Okay. Aromaticity. What do you want to remember about aromaticity? Simply that Huckel has a magic number, doesn't he? That magic number is 4n plus 2. He also has a set of rules. And the rules say that in order for something to be aromatic, it must have a continuous pi system with 4n plus 2 electrons. It must be cyclic, and it must be planar. So let's apply the test to each of these guys. First of all, this thing here does have 6 electrons in a continuous conjugated pi system, but it's not cyclic. So no, this is not aromatic. Our next guy has 2, 4, 6, 8 electrons. That's not a Huckel number. And it also has sp cubed CH's, 2 of them here in the ring. This is not aromatic. There's no continuous conjugated system that's cyclic, and it's got the wrong number of electrons. This is cyclobutadiene. Now this is planar. This is conjugated. This has 4 pi electrons. Remember, it's 4n plus 2. So this is not a Huckel number. Our next guy. We have a benzene ring. We have an oxygen attached to it. Here we have a double bond. Here we have a CH2. These guys, these side chains, really don't matter. We do have a core of a ring right here. Oh, I guess I skipped to here. So ignore that. Let's go to E. Here we have, once again, this is a cyclopentadienyl cation. It has 4 pi electrons. Once again, that is not a Huckel number. So going back to this guy, we have our benzene ring here with 6 pi electrons. This part of the molecule is certainly aromatic. These are just side chains attached to it. So the benzene ring portion of this is clearly aromatic. Yeah.
E is different
For the cyclobutyl.
from
Oh, okay, well, all right, I guess your exam has another mistake in it. On your exam, I put the cyclopentadienyl anion. So, if this was an anion, as it is in the next slide, this would have 2, 4, 6 pi electrons. Yes, it would be aromatic. But the cyclopentadienyl cation with only 4 pi electrons is not. I forgot to change that, sorry. All right, this is a different question. Here we're asking which of the following is antiaromatic. Antiaromatic means it follows all the rules except it has the wrong Huckel number. That's all it means. It follows all the other rules, but it has the wrong Huckel number of electrons. So again, this is not cyclic, just like last time. We can forget that. This has our sp cubed carbons. We can forget this guy. This has our aromatic ring. This is a Huckel number of electrons in a ring. That's aromatic. This is the cyclopentadienyl anion with 2, 4, 6 pi electrons. It is aromatic. And the one that doesn't work, of course, is cyclobutadiene that only has 4 pi electrons. Yeah?
I just am confused. If there's 2 rings, but the other one doesn't count because there's an oxygen in it, is that?
No, it just doesn't, just ignore it, totally. Forget it, pretend it's not there. We're only dealing with this as a benzene ring with things attached to it. So the benzene ring is still aromatic, it just has stuff attached to it. Now remember, we just did the lab with ferrocene. With ferrocene, the parent compound, you take 2 cyclopentadienyl anions, and you stick an iron 2 in between them. Remember, it's a sandwich. One of these on the top, iron, another one on the bottom. And both rings, of course, are fully aromatic. We did Friedel-Crafts acylation on one of the rings. Any questions? All right, your exam will also have a mechanism. Now, we've only done 2 mechanisms so far. We will do many more. We've done electrophilic aromatic substitution, and we did nucleophilic aromatic substitution. Here I'm asking you about electrophilic aromatic substitution, Friedel-Crafts bromination. Friedel-Crafts alkylation, not bromination, sorry. All right, the first box here. On the exam, you will see boxes just like this. Our first box, I ask for the structure of the electrophile as a complex with the Lewis acid. Now remember, the Lewis acid is your iron 3 bromide. Yeah.
Ours is different.
Oh dear. Oh, okay, well you have chlorine and aluminum chloride, same thing. Same thing, just different. Regardless which Lewis acid you're dealing with and which alkyl halide, what's going to happen is the Lewis acid, on your exam that's the aluminum chloride, on this is the iron 3 bromide, is going to form a complex with the alkyl bromide, or chloride, either one, you have a chloride. Same thing is going to look like this. On your exam, the chlorine would be bonded with the aluminum. Here I show the bromine bonded with the iron. This is the full complex, and this is what I would like you to put in the little box. When this forms, we put a great deal of positive charge on the alkyl group. The actual electrophile is going to be this methyl carbocation. Now, it doesn't exist as a methyl carbocation. That's too unstable. But this complex puts a lot of positive character here, and it acts as if it was a methyl carbocation. So, in electrophilic aromatic substitution, what happens is the electrophile, here the methyl carbocation, is going to add to the ring and form a sigma complex. So it's going to add to one of the ring carbons. And it's going to look something like this. When it does this, it forms a sigma complex bearing a positive charge. Now, the reason it can do this is that this positive charge is resonance stabilized. What I'd ask you to do here is to draw one additional resonance form for the sigma complex. Just one. There are 2 more, but just one. In order to do this, we have to delocalize this charge and put it somewhere. To fill in this, what I would do is just take this pair of electrons, move it up. When I do that, I place my positive charge para to our electrophile. So here it is ortho, here it is para. We could flip it again and put it in the other ortho position. But this one does. Here we have the sigma complex, and it's resonance stabilized. And the last thing I asked you here was just simply the final product. Remember, in order to get to the final product, all the sigma complex has to do is lose a proton. When it loses its proton, the electrons flow back into the ring, and we make, in this case, toluene. Any questions? Make sure you're comfortable with the mechanisms that we've talked about. Make sure you can draw resonance forms if you're asked. Make sure you understand about the electrophile itself. And how the sigma complex forms. Any questions?
Is it different from the one that we have?
Hmm?
Or is it the same kind of product?
Yep, same thing. All right, next we have some reactions. I really like reactions. Sometimes I've given exams back in 234 that had, 2 full pages of nothing but reactions. I just love that. I'm sure you do too. But here we have some reactions. Yes, artwork does matter, okay? Think about it from my perspective. If I'm grading it and I look and I see a beautifully drawn structure, I am much more likely to say, yep, that looks right. If I see something that's scribbled all over the page, even if it's right, it's probably going to be wrong. So artwork is important. Presentation matters. Our first reaction here, we have toluene and we're doing bromine ferric bromide. This is going to be simple bromination of the benzene ring. But because we have a methyl group, we need to remember methyl group is activating and is ortho-para-directing. So that means our bromine is going to go either into the ortho or the para position. Either one I would give you credit for. On an exam, it's probably easiest to draw the thing para. Doesn't matter, but probably easiest. All we're going to do here is put the bromine in the 4 position of our ring. Here we have neutral permanganate anion. Permanganate is a very powerful oxidant. Remember, we learned that any aromatic compound that has a benzylic hydrogen is a hydrogen on a carbon adjacent to the ring. If it has at least one of those, it can be oxidized by neutral permanganate to the carboxylic acid. So we do have a benzylic hydrogen here. Permanganate simply converts this to benzoic acid. Our next one, well, we just talked about this in class. Here we have an alkyl bromide and iron 3 bromide. This is going to be a Friedel-Crafts alkylation. What we're going to do here is stick on our alkyl group, which is ethyl. Once again, the methyl group that's there is ortho-para-directing. So our ethyl group is going to go in the 4 position or the 2 to give us something like this. Any question on these guys? Three more. Here we have nitric sulfuric acid mixture. We did this in class. Remember we nitrated naphthalene, I believe. We know that nitrosulfuric acid is a really nasty blend. We make HNO2 plus as our electrophile, and it's simply going to add through the nitrogen to the ring. Again, we have a methyl group that's going to direct things ortho and para. So we're going to wind up with 4-nitro. Where is it? There it is. 4-nitro toluene. Now, if you take this reaction and sit on it just a little bit, kind of warm it up, you can get polysubstitution. If we went ahead and put nitro groups, para, and put them in the 2 ortho positions, we would get 2, 4, 6 trinitro toluene. That is the explosive TNT. Our next one here, this is Friedel-Crafts acylation. This is kind of what we did with ferrocene, except with ferrocene we didn't have to use a Lewis acid. Here we do. Remember, the iron, our Lewis acid here, is going to bind with the bromine. Here we're going to form a very stable carbocation, however. This is the acylium ion. So this exists as a unique species in solution with a lifetime. Maybe 10 to the minus 8 seconds, but still it's a lifetime. This is going to add through the carbonyl carbon, once again to the 4 position on the ring, and we're going to make the acyl ketone, the aryl ketone. Remember, we can also get substitution in the ortho positions. For the exam, I don't care. Yeah?
If we draw it upside down, will you take off the left?
Of course not. Just make sure it's neat. So I look at it and I just think, it's got to be right, it's so neat. Our last one, bromo-6-cinnamide and light. I think you did this as a lab back in 234, where you did bromination of somebody. Here we are simply doing bromination at the benzylic position. This is going to generate a bromine radical, going to yank a hydrogen off of our methyl group, and we're simply going to make benzyl bromide. Simple allylic or benzylic bromination. Any questions? All right, let's move forward to cycloadditions. Remember, in a cycloaddition, we're going to have a diene and a dienophile. We're going to form a bond from the 2 terminal carbons of our diene to the 2 carbons of the double bond in our dienophile. We are going to make a 6-membered ring. It's called a 4+2 cycloaddition. We make a 6-membered ring, and we're left with a double bond. The bonds we're going to make are going to be these. Now, the dienophile that I gave you has stereochemistry, doesn't it? This is a trans dienophile. Remember the rules. The stereochemistry of the dienophile is preserved. So if we start with a trans dienophile in our 6-membered ring, we will have trans cyano groups. If it was cis, we would have cis groups. Simplest way to draw this, trans-dienophile, trans product, okay? So we're gonna form our six-membered ring this way. Our double bond is gonna be here. And it's gonna look like this. Now you can draw as a contorted chair if you want. You could use wedgies to show the stereochemistry like I did here. Wedgies are probably simpler. Again, one up, one down. These are clearly trans. These four carbons right here came from our dienophile, our diene. These two from the dienophile. Our next one. The bonds we're going to make are going to be from the terminal carbons of our diene to the alkene carbons of our dienophile. So these are going to form a six-membered ring, aren't they? The six-membered ring, however, is going to be attached to all the rest of this stuff. The rest of this stuff makes a five-membered ring, doesn't it? So we're looking for a six-membered ring with a double bond, will be right there, attached to a five-membered ring with an oxygen. Simply going to look like this. The bonds that we made in this reaction are these. Here's our diene here, here's our dienophile, our five-membered ring fused to our six-membered ring. Any questions? Now here, our diene is in a five-membered ring with an oxygen. We are still going to make our bonds to our two terminal carbons, so these two, back to this guy. So we're going to wind up with a six-membered ring with a double bond, and we're going to have this oxygen bridging the top of our six-membered ring. It's going to be a bicyclic compound. It's going to look like this. Think about the bottom here as a boat cyclohexene. And here we have our oxygen simply bridging the two end carbons on our boat. The bonds that we made are these guys. Here's our original diene on this side, and here's our dienophile on this side. Any question? All right, let's do a couple more. Here we have 1,3-cyclohexadiene, and we're reacting with a cis dienophile. Now the bonds we're going to make, once again, are from the terminal carbons to our dienophile. This means we're going to have a six-membered ring with a double bond. And because we're already starting off here with a six-membered ring, this is going to sit on top as a bridgehead unit with two carbons. And don't forget, we'll have our two nitrile groups. Product will look like this. Now, the stereochemistry here is important to remember. Here are the bonds that we made. This stereochemistry, remember, is what we call endo. It's endo. You want the pi system of your dienophile to line up, as if it can, with the pi system of the double bond that's left. Endostereochemistry, simple way to remember it is that we're above the double bond. All right, the last one here is an artistic challenge. We are going to make bonds from the terminal ends of our diene to one of the double bonds of this, which is now going to function as a dienophile. Our bonds are going to look something like this, from here and here to here and here. Now, it's a 4 plus 2, so we're going to get a 6-membered ring. The 6-membered ring is going to have a double bond right here. And we're going to have this 1 carbon bridge sitting on top of it. In addition to that, this whole chunk is still going to be there. And it's going to be attached to our parent 6-membered ring. So, artistically, it should look like this. Here is our 6-membered ring that we made, this guy. This is the rest of the junk still attached to it. And here's our 1 carbon bridge sitting up above the 6-membered ring. The bonds that we made are these guys. This is 1 5-membered ring unit, and this is the other 5-membered ring unit. Artistically, it is a very slight challenge, but I'm sure you're up to it. Any question? Now the last one here, I kind of gave away on the previous problem. But this gives you a chance on the exam to actually use your words. Okay, isn't that neat? You get to write a sentence. The sentence is why? Why do we get one of these products and not the other? What you need to do here is to simply look at them and decide how are they different. The trick here is to look at your double bonds and then look at the substituent on our dienophile. Here, the substituent, the nitrile, is above the double bond. That's endo. Over here, the substituent is simply above a saturated thing, and the hydrogen is above the double bond. Why do we get endo and not exo? Remember, the reason that we said was that the transition state leading to the endo, the pi system here in our nitrile can interact with the pi system of our diene, and that's more stable than simply sticking it out away from it. So using my words, I could say something like this. Endostereochemistry allows the pi system of the diene, that's this guy, to interact with the pi system of the dienophile, that's our nitrile group. Any questions? Well, like I said, your real exam will have 20 questions like this. It will have 2 sets of reactions, pretty much like these. It'll have a mechanism. It'll have a bunch of simple spectroscopy questions, and maybe even a chance to use your words. It will also have 2 extra credit questions. I have no idea what the point total for it is, but it's around 1 something or other. Now, we have finished this entire exam with me talking like mad in a little bit over an hour. On the real exam, I can easily imagine that you would finish it, in 15 minutes without me talking. So, you may have as long as you want, but after 15 minutes, I'm going to get antsy. So, any questions? All right, on Tuesday, we will do one more lab.